All right, so the two more topics in this chapter I really want to focus on. The first is sort of an add-on to what we did back in the aromatics chapter. We did this reaction back then, but let's go back and look at it again because it has a lot of power to it. And that is taking an amine and turning it into a diazonium salt. Diazotization. The most useful version of this, of course, is the aromatic version. So we talked about this back then. We make the nitro, we make the amino, and then we make the diazo. And then we can do lots of stuff that we couldn't really do any other way to an aromatic ring, including some regiochemical tricks we couldn't get away with any other way. So let's look at that. First, let's look at how the diazotization actually works. First, basically we're doing we're doing a nucleophilic attack on the nitrous acid, or the nitroso group, which is the active nucleophile here. Active electrophile here. Then we're basically shuffling protons around. Much as I despise that term, we're neutralizing the nitrogen, which was cationic. Then we're protonating the leftover oxygen from the nitroso group, and that eventually is going to end up being water. So it's going to give us, we're going to remove a second proton to form the first pi bond here, then protonate it a second time, and remove that entirely as a leaving group to form a second pi bond here. So here's where we get the useful stuff, though, what we can actually do with it. Now, we can actually displace that in a lot of different ways. It's called the Meyer reaction. It allows us to put a lot of different things in place. And we talked about it before. We really only dealt with the idea that we could basically use it to make phenol with. That we could basically replace that with an OH group using water. So, but that's not the only thing we can do. Specifically, Meyer reaction is about halogens. About copper salts, my mistake. So here's the idea. We can put bromines, chlorines, iodines, even nitriles in place. We don't have really an electrophilic version of that we can put in place using a Friedel-Crafts reaction or anything. And this does not play well with the type of halogenations that we generally do on aromatic rings. So yes, we have other ways to make these two from benzene. The other two are really tough. So this gives us an entryway into something that's a lot more useful. The iodide particularly gives us a way of coupling things together, which I don't know if your book covers that in this chapter or not, but aryl iodides are exceptionally useful compounds, and not really that many good ways to make them. So it's worth keeping this one in mind, that we can basically take a nitrobenzene, or take benzene, nitrate it, and eventually end up with a halogen in that spot. So it's one way of putting a carboxylic acid in place. I think this example was chosen because you can't use oxidation here. If I were to, for instance, put a ketone in place there and try to oxidize it, that same reaction would trash this. So it's a way of getting around cases where the oxidation to a carboxylic acid would destroy other functional groups. Otherwise, putting a carboxylic acid there are easier ways. But if you have functional group limitations, which very frequently you will when you're building up a complicated molecule, then you have to find backup plans to the reactions you might have wanted to do. The Friedel-Crafts acylation and oxidation would be very easy here. It would also give you something that's useless. It would not give you the right product. So sometimes the easy way just doesn't work. So we have to find a new way. And this is one way to do it, is that you're then replacing this with a nitrile group, which they're not showing you the intermediate step here, but you end up, here. And then you're hydrolyzing that with this step. So relatively simple. Okay, other stuff. This is the one we had talked about before, which was we can heat it up with water and get a phenol. You can also do a fluoride one. This one is not as common, but again, it does come up because fluoride groups, just like chlorine and just like what I said for the iodide, really you don't want to be doing that directly because fluorine is a gas for starters. So halogenation with that is not pleasant. It's a dangerous gas to handle. So, and this is much simpler and safer. Rarely you're going to reduce it down. Again, you could do this. It's not generally something we spend a lot of time on, but it is a useful trick when you want to use it as a directing group, and that's what we're going to see at the bottom half of this. Now, we're not saying a whole lot about this, but notice what's happening. If I gave you this to make before today, you'd have no way to do it. A bromide is an ortho and para director, and that's all you have there. So you know how to put those in directly, but you'd never get this product out of it. Never. So you have to put something there to alter the directing group trick. This is one way to do it, is that you're putting the amino group in place, using it as an ortho and para director, which means that these are now meta to each other, despite the fact that if I put them in by themselves, they would never go that way in a benzene without an amine present. And then going through a two-step procedure to make that into a diazonium ion and then remove it. So we occasionally have to use a trick like this. We have to use some temporary group to help us direct the groups we really care about to the right spots. So this is a good example of it. It gives us the ability to put groups in place that we could have never put in directly in the relative orientation that they're in. So these would never have gone in meta to each other. Never. If we try to do it directly from benzene. But because this is here, well then they're going to go in meta to each other, and then we say bye-bye to that with the last steps. So it's a very useful trick to change the direction. We did some of this before. Back when we did the aromatics chapter, we talked about how some things are aromatic by resonance, and that we have some questions about what is and what isn't going to be aromatic lone pairs. So, the idea that if an aromatic ring has something other than carbon in it, we call it a heterocyclic ring. So, things with oxygens, nitrogens, sulfurs that are aromatic, even ones that aren't aromatic, actually, we call them heterocyclic. But the point that we really care about here is that we're going to talk about aromatic ones primarily. They're choosing two examples, and both of them are a little bit strange. The first one, Nexium, this is a chiral molecule, and it's chiral to sulfur, which they're not drawing. It's a very interesting chiral center. It's also one of the dirtiest patent games ever played in the history of pharmaceuticals. It works very slightly better than the racemic mixture, and it costed, when it came out onto the market, about 10 times as much for something that can actually be made less expensively than the original racemic version. So it proved that AstraZeneca, that owned it at the time, really knew how to make a profit. It does work very well for healing acid reflux damage and ulcerations, but the actual marketing on it was a little bit disingenuous and definitely a little bit weird in terms of making something more cheaply and charging inordinately more for it. But business is business. That's your job, I suppose. The other one is the most famous side effect in the history of medicine. It also is a change in a lot of different things. First, unfortunately, they gave you the name on it, so I can't really pull that on you. You know what this is used for. This is erectile dysfunction. It's the most famous and the first one that hit the market. It's actually a phosphodiesterase 5 inhibitor. But the part about it that's actually legend, and one that I would love to read the doctor's notes on, is the clinical trials for it. It was originally, because it's about blood vessel constriction, it was originally designed to treat angina. So basically your test subjects would have been probably largely old men with heart issues. And so you go and talk to them, okay, do you have a headache? Do you have, tingling in your fingers? Typical drug side effects that you're exploring. Do you have numbness? Are there any other side effects? Yeah, doc. So I can picture someone like, my grandfather being a part of a clinical trial like this and having to tell the doctor the side effect, which is what they eventually ended up marketing it for. It does not work very well for treating angina, but its side effect turned out to be something that was massively marketable, and now there's a whole set of these that are used for that same disorder. But the point is, it's a very good example of life giving you lemons, you make lemonade. Well, this failed at the actual design target, but it had other side effects which turned out to be massively marketable. Pay attention to something that goes wrong. It may make you the biggest drug at the time that was on the market, even though it failed miserably at its original design purpose. The point is, documentation is your friend. Don't just write down, it didn't work. Write down any other observations that might be useful, both in a laboratory setting and definitely in a clinical trial setting, because maybe you find something else to use that molecule for. Maybe the money you put into the development here didn't go to waste. It certainly didn't for Pfizer when they marketed this. All right, so a few things to talk about. One, halogenation, or at least electrophilic substitution for pyrrole. Works very well. Same is also true for indole, which has a benzene fused onto the side. Works very, very well, and very predictably to certain spots. For pyrrole, it goes here because of resonance. For indole, it goes here for the same reason. So that might mislead you at first into thinking that I can just take any nitrogen heterocycle and make it work because the nitrogen's an electron donor. Remember, this particular one, actually both of these particular ones, the lone pair is part of the aromatic system. It's already tied into donating into resonance to begin with. So if I were to take this, for instance, and try to do that same reaction, if it works at all, it's going to work very, very poorly. Because this lone pair is not part of the resonating system. This lone pair is not part of the aromatic system. So you have a normal, stable benzene system here. You're going to have to beat on it to make it work. The pyrrole system, because you actually had a smaller ring and a lone pair as part of resonance for it, this is actually really, really easy to do. This is an easier halogenation than benzene. Because, for starters, you have more electron density. Your 6 pi electrons are spread only 5 atoms, so each of them is a little bit richer. And second, because you already have a resonating pair of electrons, a resonating lone pair as part of the system to begin with. All right, so second one that comes up a lot, imidazole. This is, if I had a carboxylic acid here, that is histidine. The decarboxylation gives us something that a few of us know very well, histamine. This is part of your allergy response. And there's a whole class of drugs that are made just to block this, called antihistamines. But the point is, this is the signaling molecule that's part of your runny nose, your reddened eyes, your sneeze reflexes, postnasal drip. All of that comes out of your histamine response. And so if you block histamine receptors, you stop all of that. It actually turns out there's multiple types of those receptors. One of them is responsible for stomach acid, which is, to double back a couple of slides, how we ended up with omeprazole in the first place. Was somebody trying to refine the older type of antacids that were histamine blockers, and they're still used. Pepsid, Tagamet, and Zantac are the 3 that are your common stomach acid histamine blockers. And then you have Benadryl and Claritin, Zyrtec, and things of that nature that work on the respiratory and nasal passage histamine receptors.